This is the quiz on matter and energy. These first two questions refer to Millikan's oil drop experiment, which you probably didn't do last year. It's in the packet, and there's a video. You read it through once, and you don't spend more than 3.5 minutes on it. Will it be on the AP exam? I don't know. Maybe one question max. So it's definitely not something that's worth more than like 3.5 minutes of your time. Basically, Millikan was trying to figure out the exact charge on an electron. We knew electrons were negative, but he wanted to know like how negative is an electron. So he had this experiment where he put radiation into this chamber and ionized the air particles, which means he turned them into positive ions and removed electrons. So then he sprayed a really fine mist of oil droplets into this chamber, and the negative electrons were attracted to the oil droplets. And it turns out then that the charge accumulated by these oil droplets always came in whole number quantities of this. So question one, every oil droplet had an integer number of electrons, a whole number of electrons, and the charge on the oil droplet was always some whole number quantity of this negative 1.6 times 10 to the negative coulombs per electron. Coulombs is just a unit of charge. That number's in the packet. So if they ask anything about this oil droplet experiment, because they've still kept that number in the packet, which kind of surprises me, it maybe would be a question like 2. An oil droplet had accumulated a charge of negative 4.8 times 10 to the negative 19th coulombs. How many electrons had accumulated on the oil droplet? Just divide by this charge per electron that's in the packet. And eventually we might use this guy a little bit when we do some electrochemistry, like what's the charge on a group of electrons. But this is maybe the type of question you would see, only because they still have that number, the charge on an electron, in the equation packet. So it's not meant to be anything tricky. You just look it up, and it should always be some kind of a whole number ratio of that charge. Question 3 is the photoelectric effect, where we can prove that different forms of electromagnetic radiation have different frequencies, wavelengths, and energies. So there is energy that's shined on the surface of the metal. When the metal surface is exposed to light with increasing frequency and energy of photons, electrons first begin to be ejected from the metal when the energy of the photons is 3.3 times 10 to the negative 19th joules. And we're looking for the frequency of light. And so here's one of the equations in this section of the equation packet. The atomic structure section has 2 equations. E is energy of a photon equals Planck's constant times the frequency. And they'll remind you of what these variables mean in the packet if you forget that this little Greek V is the frequency. It's in there. They tell you Planck's constant is 6.626 times 10 to the negative 34th joule seconds, which then kind of reminds you that E, the energy of a photon, needs to be in joules. If by chance it would have been in kilojoules, you'd want to switch that so that joules of Planck's constant equals your energy value in joules. Now you just plug it in and solve for the frequency, no big deal. It's in units of 1/seconds, waves per second, cycles per second, seconds to the negative first. This type of a calculation would now be free response, but if you pulled out your calculator, totally fine on this particular question. Here's the other equation in this section of the packet. Speed of light equals frequency times wavelength, which they'll give you the speed of light, 2.998 times 10 to the 8th meters per second. This case, I have a frequency and I'm solving for a wavelength. So I just need to know now that because the speed of light is meters per second, my wavelength will be in meters. And if given an electromagnetic spectrum, I can find the type of radiation emitted. this would be visible green light. And again, another question that would be free response, because you probably want a calculator for this. Same thing with 5, right? This is totally free response. This screams free response. Here's a combination of both of those equations. I have a mole of photons of blue light that have a wavelength of 450 nanometers. And eventually I want to know the energy of these photons. Okay, well, energy is Planck's constant times the frequency, but I don't have the frequency, I have the wavelength. So we can use that red equation to solve for the frequency. We know the speed of light. We can look that up in the packet. The only problem here is that our wavelength is in nanometers, and we need to switch that to meters. And they do not give you that conversion between meter and nanometer in the packet. So you have to know that a meter is 10 to the 9th nanometers, which like 9th, nano. Most people remember that. Then once you have the corrected wavelength in meters, you can solve for the frequency, about 6.7 times 10 to the 14th 1 over seconds, cycles per second, waves per second. And then once I have the frequency, I can plug it into the blue equation. Energy equals Planck's constant times my frequency. Now, FYI, when you calculate energy, it'll be in joules, because Planck's constant is in joules, and it'll be joules per photon. So you have to just be careful, because if they ask for this energy value in units of like joules per mole of photons, well, now you're going to need to multiply by Avogadro's number. Or sometimes they might want the energy in units of kilojoules per mole. Well, this is going to come out in joules per photon. I'd have to switch it to kilojoules and then multiply by Avogadro's number. Just be a little careful. That's maybe the only thing that sometimes catches us. This is per mole of photons. And the answers are all in joules, so I didn't have to worry about the joules or kilojoules. All of this is in the packet. All the equations, all the variables, all the constants are in the atomic structure section of the packet. Okay, and then a couple of these at the end. These were questions that high school teachers were like, what? Like, we don't have the equipment to like graph any of this in our labs. And college professors said, but it's an application of the electromagnetic spectrum. And I think some of it comes up now, and some of it's a little bit more applicable once we do bonding. But here's the deal. To prove that different types of electromagnetic radiation carry different amounts of energy, you'll see different types of changes when a substance is subjected to these different forms of radiation. Here are the 3 that they want you to know. And I think the one that we're maybe ready for now, we're most ready for now, is that region X. So if I have element, molecule that is absorbing ultraviolet or visible light, that's the type of energy that causes electrons to move up and down the energy levels. So X causes electronic transitions. And that's what we've done. Like, we demoed some of this, that, you know, if you do a flame test and you have a compound or a metal and you excite the electrons, often light is released in the visible light spectrum, that we could see the green flame or the orange or the purple or the like the red of lithium. And it could also be in the ultraviolet spectrum, which we just wouldn't see. You could see that with the emission tubes when we wore the spectrum glasses, those prism glasses, that light was emitted in the visible light spectrum. And ultraviolet, we just can't see it. The other 2, infrared and microwave, are a little bit more applicable once we've done bonding. But here's the deal. I mean, obviously now energy is decreasing. Microwaves of these 3 have the least amount of energy. So if you submit microwaves on an element or a compound, you'll see like the least intrusive change. And all that's going to happen is that molecules rotate a little bit in region Z, this microwave region of the spectrum. Molecular rotations are a pretty minor change. Single bonds can rotate, and we'll do it like once we build structures, model kits, and we're doing bonding, that you can rotate, like you can twist a single bond, but it really doesn't cause a change to the properties of the structure. It doesn't change the bonds and make them stronger or weaker. It's just like spinning atoms on their single bonds. So the lowest energy, the microwaves, causes the lowest change. Molecules just rotate a little bit. Then in the middle, the infrared radiation causes molecules to vibrate. And I mean, they always vibrate a little bit within their bonds because there's always this struggle between attraction of oppositely charged nuclei and electron clouds versus repulsion of like-charged electron clouds and nuclei. So all molecules vibrate a little bit, but when you add energy in this infrared spectrum, you increase the degree of molecular vibrations. And eventually, depending on how much energy was added to cause these vibrations, we can predict if the bonds are like single bonds, double bonds, triple bonds, with like a triple bond being stronger and requiring more energy to cause vibrations. But I think for sure if you get that the visible and ultraviolet is associated with electrons moving up and down the energy levels, right there, that narrows it down to a 50-50 guess. And then you kind of remember that then it would go vibrations, and the lowest change would be just a rotation. And this is a good question. This is a pretty recent question. Same thing with 7 and 8. It's the same stuff, just in a different way. Nitrogen molecules absorb ultraviolet light, but not visible, both of which would be associated with electrons transitioning up and down the energy levels. So for nitrogen, ultraviolet light will cause electron transitions, but not visible. Iodine molecules absorb both visible and ultraviolet light. Both cause electron transitions. The correct choice here is the third. Visible light does not produce transitions between electron energy levels in nitrogen, but it does produce electron transitions in iodine. Great question. Knowing that it's these electron transitions that are caused by ultraviolet and visible light. And then 8 is asking about infrared radiation. Infrared being kind of in the middle if I'm comparing the visible and ultraviolet, highest energy. Then would come infrared. It means like below red. And then weaker than that would be like your microwaves, or even weaker would be a radio wave. Infrared spectroscopy is a useful tool for scientists who want to investigate the structure of certain molecules. Which of the following best explains what can occur as the result of a molecule absorbing a photon of infrared? And so we said infrared radiation should be associated with those vibrations. And it says then in that second choice, the energies of infrared photons are in the same range as the energies associated with different vibrational states in chemical bonds. Molecules can absorb infrared photons of characteristic waves, thus revealing the types and strengths of different bonds in the molecule. So this can help us figure out if they're single, double, triple, to see like how much energy do I have to add to cause these vibrations to occur. And then the lower energy would be like the microwaves, and that would just cause those weak transitions, or not even a transition, where bonds rotate a little bit, like a single bond. You can twist it and rotate it. A pretty low invasive change on the structure and function of a particle.